When you're looking at the nebulae, you notice that you got the bright glowing patches. That's mostly gas, hydrogen. We also know there's other things that are in there. Radio telescopes, we can see some other molecules that are in there. And so question is, what makes up a nebula? Well, most of it is hydrogen. 90% of it is hydrogen. Over 9% of it is helium. Only less than 1% is typically anything else. And that other stuff is things like carbon and iron and oxygen and so forth, silicon and things of this sort. Basically, the basic stuff that makes up most of the solar system. And often these other things will congregate. For example, if an oxygen finds some hydrogen, it'll bond to it and make water. Carbon that finds a hydrogen can make methane. Carbon that finds a nitrogen can make ammonia, and so forth. And so you have these other little molecules that form in here, and then they start sticking together. And as they start sticking together, they have these little strings of molecules they're not really a chemical or anything. They're just a bunch of molecules, hanging out with each other. We call that interstellar dust. Okay. Typically, iron is going to be a main constituent of the interstellar dust. And then you have water and silicon and ammonia and methane and other sort of stuff stuck to it. And so iron and silicon, and then water, ammonia, and so forth. The water, the ammonia, the carbon dioxide, CO2, carbon monoxide, all this sort of stuff turns out to actually outnumber the silicon and oxygen, or rather the silicon and iron typically, but all this stuff together makes interstellar dust. Well, that interstellar dust actually blocks light pretty effectively. And so the molecules don't actually want to stick to each other very easily. And so what happens is that with a warm nebula, they don't stick together, but with a cool nebula, they will stick. And so often the dark nebulae are cooler, and that's where you get a lot of interstellar dust. Okay, in fact, we call them dust clouds. And many of the dust clouds tend to be cooler than the H1 or the H2 regions. And the interesting thing is that the Horsehead Nebula, it says here, is Barnard 33 against a backdrop of IC 434. What does that mean? IC is index catalog. This is the supplemental catalog to the NGC. The new general catalog, and so there was a little bright patch in the sky in Orion. They named IC 434. Emerson Barnard, an American astronomer, was really big on looking at these little dark patches in the sky, and so this was number 33 in Barnard's list of little dark things. Coalsack Nebula, this is one of the southern hemisphere. It's called C99, Colander 99, Colander being another person that did this. And all this dust out here in space will actually block our view of the rest of the galaxy. And so here is a galaxy on the right that's very similar to what our galaxy would look like. And you can see the dust lanes, which are running down the middle of it, and those dust lanes running down the middle of it block the view of some of the other stuff, the stars that are in there. And again, spiral galaxies have the bright spiral arms, for they also are clumpy with dust. Okay, so the ionized gas tends to be very, very hot. Because you're ripping electrons loose from the atoms, and that takes energy to do that. Neutral gas we call warm for astronomy, and it's warm because the molecules still have enough energy so that when the molecules start coming together, they'll bounce off of each other rather than coming together for a molecule. If they're cool enough, the molecules will come together and stick, or the atoms will come together and stick and form molecules, and the molecules will come together and stick and form dust. And so the dust clouds and molecular clouds tend to be cold. The neutral hydrogen that's not forming molecules, is warm, and so forth. Discovery of the interstellar dust, interstellar medium, actually goes all the way back to the 1940s, a fellow named Robert Trumpler. And he was looking at star clusters. And when he was looking at star clusters, he noticed some interesting things about star clusters. And that is that when you look at star clusters, that there's different ways of measuring distances. One way is to look at the size of the star cluster, and the other way is to look at the brightness of the star cluster. And he noticed that these two methods didn't seem to work. In other words, you could look at a star cluster and say, okay, we have the smaller a star cluster is, typically you'd expect the farther away it is. The dimmer it is, you'd expect it farther away. So what he discovered was that distant star clusters, that if you're pretty nearby, then the two methods gave the same results. But if things are really far away, the far star clusters were too dim. So in other words, the distance you measured using the brightness method was a lot dimmer than the method you used by measuring the size method. So what does that mean? Well, it means that either those star clusters were unusually big, and so the size method was making them look too close, or the stars were too dim, and so that was making the distance method too big. Well, he thinks about this and said that doesn't make any sense. The distance that a star cluster is from Earth has nothing to do with how big it actually forms. Likewise, the physics of how the stars work should be the same everywhere, so it doesn't make any sense that stars shine dimmer depending on how far they are from Earth. So the only thing you think of is there's something between us and the star clusters. And so you have these distant star clusters, and we look at them, and there's something in between that the light is shining through, and the farther away the star cluster is, the more of that something is, and the more it's dimming the light. And so that became known as the interstellar medium. So the interstellar medium, light shines through it, and it does two things. It makes the stars look dimmer, but it also absorbs the blue light more than it does the red light, and so it makes the stars look redder. So the interstellar medium does two things: interstellar reddening and interstellar extinction. So the extinction is the dimming effect, and the reddening is obviously making it look redder. And so these are the two effects of the interstellar medium. What's the interstellar medium made out of? Well, you can look at the spectral lines of the interstellar medium, the light that does shine through, and find out what's missing, and you find out it's mostly hydrogen and some helium and a little bit of that dust. Well, when we map the interstellar medium, we actually notice some interesting things. It turns out the region of space where the sun is actually thinner than normal in the galaxy. So we have this large region that's somewhat thinner than the rest of the galaxy's interstellar medium. Well, turns out the galaxy actually has several of these large thin regions. The thin regions tend to be a little bit hotter gas that's moving around a little bit faster, and we call them bubbles. So the bubble that surrounds us we call the local bubble. Again, astronomical way of naming stuff. Keep it simple. Okay, local bubble. Now, turns out that very close to the sun's right here, very close to the sun here is a region here that is a little bit thicker than the rest of the local bubble, and that is called, yes, the local fluff. Okay.